Okay, I would like to then begin the next session. So we have three speakers, very interesting topics, all related to relativity in some way. The first pertains philosophical aspects, and the next has to do with general relativity in some way, and the third has to do with special relativity. So the first speaker is Peter Achinstein. He's professor of philosophy at Johns Hopkins University. I'm using the modern method in reading notes. And he is also the director of the Center for History and Philosophy of Science at Hopkins. He authored 6 books in the philosophy of science, including one titled Particles and Waves, which won the Lakatos Award in 1993. And at Oxford there was a festschrift in his honor, and there was a publication titled Philosophy of Science Matters, the Philosophy of Peter Achinstein. So what he's going to talk about today is something I've always been kind of curious about when physicists say, well, I just look for the simplest theory. I wonder, what do I mean by simplicity? So I'd like to then present Peter Achinstein. The title of his talk is Science and Simplicity.
Okay, thank you very much, Larry. Well, keep in mind I'm a philosopher talking to mostly scientists, I assume. And scientists seem, as Larry said, to get very excited about, especially physicists, about simplicity. They think it's, it's the sign of what? I don't know, truth, beauty, whatever. And it's a necessary condition. And I want to talk about this because I'm very skeptical about what has been said by even the greatest scientists about the notion of simplicity. My two favorite scientists who really believe thoroughly in simplicity are Isaac Newton and Albert Einstein. And so I'm going to talk a bit about what they say. My question really is, look, even if we could define simplicity, and nobody has ever achieved that goal, even if we could define it, what do we do with it? What's it good for? So Einstein appealed, let's see if I can work this thing. Here's the views I'm going to discuss. Einstein appealed to simplicity in his writings, throughout his writings, over the years. He was influenced by a physicist, a philosopher, and historian of science, Pierre Duhem, at the beginning of the 20th century, in his great book, The Aim and Structure of Physical Theory. And Duhem said scientific theories are underdetermined by the evidence. Given all the empirical evidence and all the experiments we have, they won't point, logically speaking, to one theory rather than another, and therefore you have to use the criterion of simplicity in choosing among these possible theories. And Einstein liked that idea early on and even later on in his life. Okay, Einstein said, like I would say, I think, following him, that I'm not going to define simplicity because I don't know how. But what I do know is how to recognize it when I see it. Okay? And so I'm going to adopt that same attitude. And I tried to think about what do you do with simplicity? What's it for? Why do you even bring it up? And there are 6 views that I thought of. I don't know if I'll get through all of them, but I do want to get to the 5th one, at least the pragmatic view. The first is the ontological view about simplicity. And let's see if I can... Sir Isaac, there he is. In the Principia, just before he proves the law of gravity in Book 3 of the Principia, he makes these 2 statements in the rules of reasoning that he says he's going to use. There are 4 rules of reasoning. He actually uses them in the proof. and one of them is this principle of simplicity, don't multiply entities beyond necessity, so-called Occam's razor. And he justifies that by saying that nature is simple and does not indulge in the luxury of superfluous causes. And then when he establishes the law of gravity for the planets and their moons, and he wants to generalize like mad to all bodies in the universe. He uses this principle of induction, which he justifies by saying nature is always simple, ever consonant with itself. Here's Albert Einstein, who says that as nature progresses, apparent chaos is resolved into a sublime order that is to be attributed not to the rule of the individual mind, but to the constitution of the world of experience. This is what Leibniz so happily characterized as pre-established harmony. Okay, so you have these great giants saying that the world itself is simple. That's one view. Now, the next view is a little bit different. The next view really was propounded in the best way, I think, by William Whewell, who was a scientist. He was a master of Trinity College in Cambridge University in the mid-19th century. And Whewell wrote that we have to notice a distinction which is found to prevail in the progress of true and false theories. In the former class, all additional suppositions tend to simplicity and harmony. In false theories, the opposite is the case. And Einstein also is of this view. Einstein says, our experience hitherto justifies us in trusting that nature is the realization of the simplest that is mathematically possible. In other words, simplicity is a very good indicator, in your theory, is a very good indicator of the truth of that theory. That's the view. Okay. Now, a third view was the one that given by Pierre Duhem, whom Einstein really liked to read, about the aim of science. It's a much broader view. And it says the aim of science is to provide the simplest theory that will enable us to derive the observable facts. And Duhem wrote that a physical theory is a system of mathematical propositions deduced from a small number of principles which aim to represent as simply, as completely, and exactly as possible a set of experimental laws. Okay? And Einstein, following that, says the preeminent goal of science is that of encompassing the maximum of empirical contents through the logical deduction with a minimum of hypotheses or axioms. So it's the aim of science to get at simplicity. Whether or not nature is simple is another matter, but at least we should aim to provide the simplest theories. That's the third view. Now, the fourth view is a little bit different. It says that science itself presupposes that the world is understandable. When you do science, you presuppose, you can't do science without presupposing that the world is simple. And this is Thomas Nagel, a contemporary philosopher who wrote a book, Mind and Cosmos, and tried to show that what is needed to combine the mind and the body and physics is a physiological, teleological theory which can explain everything, a theory of everything. Einstein and Infeld write that without the belief in the inner harmony and simplicity of our world, there could be no science. So that's another view. And let's see if we can get the pragmatic view. And I want to talk about this. I hope I can get to this. The theories that have simpler equations, make fewer assumptions, and postulate fewer entities are easier to use for various purposes, including explanation and prediction. They're easier to develop further, and this view does not assume that the world is simple. It just says, look, we want to, for pragmatic reasons, we want to supply a simple theory, simple formula, simple laws, and so forth. And the final view, with all these pictures in it, is simplicity is an aesthetic virtue. It's just beautiful to have a simple theory. It's worth having for its own sake. All right, those are the positions that I distinguished in looking at the literature on simplicity, about the role of simplicity. Now, none of these theories define simplicity as such, but they all have a very strong view about the value, what you're trying to do with simplicity. Okay. So let's look at the first view, the Newton view here. If I can get to Sir Isaac. There he is, and that's Newton right there. And I want to be critical of all these views. Okay? And what I want to say is, first of all, what does it mean to say that nature is simple? Newton. These are direct quotes from Newton. Nature is simple and does not indulge in the luxury of superfluous causes. What does that mean, to say that nature is simple? Well, there are various types of simplicity. For example, simplicity with regard to the numbers of different entities postulated. For example, string theory says it's simple because it just postulates the existence of strings. Whereas the standard model, they have lots of animals in the zoo there. And so, is it simplicity with regard to the number of things? Perhaps it's simplicity with regard to the number of different laws that are needed. Simplicity with regard to the mathematical expressions. Does nature is simple mean it's simple with respect to all of these things, with respect to some of these things? And also, I take it there are degrees of simplicity. How simple is nature supposed to be? These are questions I would have for anyone who says nature is simple, including Einstein and Newton. But the more important question I want to raise with you about this view is, how do you know nature is simple? Even if you tell me in what respect it's simple and how simple it is, how do you know that? And interestingly, neither Newton nor Einstein give any answer to this question. Okay? Newton just puts it down there, and as far as I can tell, so does Einstein. So I have to make up an argument, okay? Because these are fundamental views that these physicists hold. And the only argument I could think of is that an inductive one, that in the past simple theories have been empirically successful. They made good predictions. So probably nature is simple. That's a simple inductive argument in favor of the ontological claim that nature itself is simple. The problem with this, as I see it, is lots of simple theories, in simple and obvious respect, have turned out to be empirically unsuccessful. I mean, let's go back to ancient Greece. Thales said, there's one element on it, and that's water. Everything is made of water. Well, that's as simple as you can get, I suppose, and that's not very empirically successful. Aristotle multiplied it by 4. He's got 4 elements: earth, air, fire, and water. Right? Very unsuccessful, very empirically unsuccessful. So simplicity, I think, is, and you can multiply the examples very easily. Simplicity is not a good predictor by itself of empirical success. Indeed, sometimes equations that are quite complex are closer to the truth than simple ones. Just take, for example, the ideal gas law, a very simple expression relating pressure, volume, and temperature of gas. Not very successful in predicting what's going to happen, especially at the extremes. And what's much more successful is a more complex virial equation which brings in intermolecular forces. But it's, as I say, much more complicated. So I'm not going to buy this inductive argument that simple theories turn out to be right. Sometimes they do, sometimes not. Sometimes you need a much more complex theory to get what you want. Now, interestingly, Newton and Einstein, neither of them can give this inductive argument. They can't support the idea that nature is simple by saying, well, our simple theories have worked better than our complex theories. Even if they haven't, they can't give the argument because Newton, it's an inductive argument. And Newton uses the claim that nature is simple to support induction. In other words, he wants to say, look, I've proved the law of gravity for the planets and their satellites, and therefore, by induction, I'm going to assume that the law of gravity holds throughout the universe. That's exactly the way his proof goes. So he needs induction to generalize like mad, the way he wants to do with the law of gravity. And he supports induction by simplicity. Well, so if he were to give an inductive argument, the argument would have to be circular, because he'd be using induction to support simplicity and then using simplicity to support induction. So he can't do that. And Einstein can't do it either, because Einstein says that theories are underdetermined by empirical evidence. So he can't infer that nature is simple based on the evidence, the inductive evidence of successful theories, without invoking simplicity, because induction for Einstein doesn't give you what you want by itself. You have to add simplicity. Remember, theories are underdetermined by the evidence. So the way you get to a theory is by picking the simplest theory and saying that's the best supported. So he can't defend simplicity by induction, because induction doesn't give you the theory that you want. All right. So finally, well, where does a claim come from? How do you defend the claim, even if you knew what it meant, that nature is simple? Well, I suppose you could follow Kant and make it an a priori judgment, right? And Newton would have turned over his grave if he heard that answer. For Newton, science and the scientific principles underlying it are all empirical claims. And I think the same is largely true for Einstein. So an appeal to Kant's view about this is a synthetic a priori judgment about the world would have been anathema to both of these great physicists. Okay, let's go on a little bit here. We got Einstein, we got Whewell. Okay, no, we're skipping too much here. Let's get to the epistemological view. If a theory is simple, that's a good basis for believing that it's true. And the simpler the theory, the more probable it is that's true. That comes from Whewell, but a lot of people believe that, including Einstein. And I want to know, why should I believe that? If it's simple, even if I understood the notion of simplicity, if a simple theory, if you have a simple theory, it's more likely to be true than a complex one. There's no argument given by Whewell or anyone else, so far as I know. So I'm going to make up, well, actually there is something that Whewell says. So here it is. It's called a no miracle argument. Okay? Let's see if I have that down here. Analogical view, no miracle argument. Okay. It says the following. The theories that are simple have turned out to be much more successful in their predictions than theories that are complex. Let's assume that were true. I don't think it is, but let's assume it's true. Theories that have been turned out to be successful, that are simple, have turned out to be successful. This demands an explanation. Why is it the case that simple theories have turned out to be true more than complex theories? This calls for an explanation. It's no miracle. Not by chance. It's no miracle. The simplest explanation is that such theories are true. Why have simple theories turned out to be true? Because such turn out to be empirically successful because they're true. This argument is circular. It appeals to simplicity in defending the idea. So you're not going to get to first base defending that kind of an argument. Also, the premise is false, as I've indicated. The theories that are simple have turned out to be true much more regularly than theories that are not. I haven't counted up theories. I don't know how you do that, but for any simple theory that you think is empirically good, I can find one that has not worked. Okay. Now, I want to get to the more important one, the underdetermination argument. The underdetermination argument says that theories are underdetermined by observational results and experimental evidence. So if we're to believe a theory true or probable, there must be some criterion on the basis of which we choose among these various possible theories, all of which are consistent with the evidence. And that criterion is simplicity. Okay. In other words, we have to use simplicity if we're going to get any place in our theorizing. So here I want to ask, what does underdetermination mean? It's an idea that comes from Duhem. It's stated by Einstein that empirical evidence, experimental results are not sufficient because there are various possible theories that fit in with the experimental evidence. You need simplicity. That's underdetermination. So what is underdetermination? Well, there are two possibilities. One is that the empirical evidence by itself is not sufficient to make the theory more probable than not or more probable than competitors. Well, okay, if that's true, then we should be agnostic. If all the empirical evidence we have doesn't support one theory more than another, then we should say we don't know. It's like coin tossing. Okay, you tell me you're going to toss a coin. It's going to be a fair coin, a fair toss, and that's the evidence you have. Now that evidence doesn't point to heads, doesn't point to tails. So what do? We say, well, let's pick the simplest one. I don't even know what the simplest one would be in that case. But that's clearly not what we do. What we do, and that's what makes for games of chance, is say, we don't know. Let's toss the coin. Okay? So I think that's, to me, the simplest thing to do, if you want to talk about this in terms of simplicity, is to do nothing. Okay? Not to say, let's pick the simplest theory and claim that it's the one that is to be believed. All right, let's go to the other side. Suppose the empirical evidence makes a given theory highly probable, but doesn't establish it with certainty. Okay? Okay, so that could be what underdetermination means. It means you have a bunch of evidence that makes your theory quite probable, but it doesn't prove it to be true. It could turn out to be false. Okay, again, I'll give you a simple coin tossing example. Suppose I have a biased coin, okay, very biased, and it's 95% biased towards heads. Okay? And so if I toss the coin, what should I believe, heads or tails? Well, in this case, I have a huge body of evidence, let's say all the evidence that supports the bias, to say that it's going to land heads if it's biased towards heads. 95% bias. Then I don't need simplicity at all. I just look at the evidence. Very seldom do you have evidence which is absolutely conclusive in this way. So the underdetermination argument doesn't seem to work, in my view, at all. Either you have enough evidence, in which case you make the conclusion, draw the conclusion without appeal to simplicity, or you don't have enough evidence, it goes either way, and then you don't make any conclusion whatsoever. Okay. The aim of science view. Let's see what we got here. Oh, yeah. All right. Okay. Now, the aim of science view says that it's the aim of science to provide the simplest theory possible. Okay. But you could add other criteria, beautiful, coherent, unifying, and so on, but I'm concerned here with simplicity. Okay, now, my initial response is that can't be quite right, because if you want to get very simple explanations, you read the Encyclopedia Britannica, okay, or Scientific American, although that's become quite complex these days. But no, that's not what these guys mean. What I think these guys mean is something much more interesting. That is, that the aim of science is to provide a unifying, simple explanation which can really explain everything. Okay, one theory. It's simple in this important respect that all you need is one theory to explain everything, a theory of everything. And this is what some string theorists have said about string theory, that it's a great theory because it provides a theory of everything. Okay. And they say, these string theorists that I'm talking about say that there must be such a theory in nature itself, even if we haven't yet discovered it. So a theory of everything deals with the simplest and most fundamental objects in the universe, say they're strings, of which everything else is composed, subject to the simplest, most fundamental laws governing these objects and all other objects too. Theory will explain everything. Okay. Along with this idea is that the presupposition view, which is that science presupposes that there is such a theory. That was Nagel's idea, that when you do science, it's not simply the aim of science to get to this theory, but you can't do science without presupposing that there is this one grand unifying theory, simple theory. Okay. Now my response to this, this is an interesting claim because it really is a very, very strong form of reductionism, which is quite controversial. My first claim is there's no good argument that I could find for thinking that a theory of everything exists, or even that if it does exist, that we'll be able to find it. Every time in the past there haven't been too many theories of everything, but I'll mention two of them. One is Aristotle's teleological theory of nature, which he thought could pretty much explain everything in terms of the four causes, including the final cause of nature. That doesn't work very well. And the other one, 17th century mechanical philosophy, so-called, the kind that Newton espoused, that says that everything can be explained in terms of forces acting on bodies subject to Newton's laws of motion plus gravity. And that doesn't work that well. So if you might say that you might adopt what you might call a pessimistic induction. The theories that have aspired to be theories of everything, very simple theories with few laws and few entities and so on, have not worked. Why suppose then that this one will, or that there is one, even more importantly? In fact, I'll go beyond this and say something perhaps controversial. There's no reason to suppose that everything is explainable in the universe. Perhaps there are things in the world too complex to explain, or perhaps parts of the world are too disorderly to explain. It's not a priori true that everything can be explained. It's an empirical claim, and one that is still up in the air. Even if everything in the universe can be explained, my third point is, how do you know it can be explained by one single theory? Maybe you need a lot of different kinds of theories to explain different sorts of phenomena. The theory of everything theorists assume there's one grand theory, not just that everything is explainable, but there's one grand theory that explains it all. So that's the claim that I am questioning now. And finally, in this regard, explanation, something that is dear to my heart. The concept of explanation is itself pragmatic. You explain what you need to explain at the level you need to explain it. And my favorite example is Newton here. Newton derives the law of gravity at the end of the third book of the Principia. And then he has a general scholium, which has become famous, in which he says, look, I have explained the motions of the planets and their satellites. I've explained the motions of bodies on the Earth. I've explained the motion of our moon and so on, and the tides. But I cannot tell you, I have not explained why gravity works. And I don't know. Okay? And famously he added, hypotheses non fingo in Latin. It's translated as I don't feign hypotheses. I'm not going to make up a hypothesis because I can't prove it. I can't give you any evidence for any theory that I can come up with. In fact, I can't come up with a theory about the cause of gravity. But Newton said in Latin, satis est, it is enough. It is enough that I have proved that the law of gravity is true. And it's enough because that's what I was trying to prove. The whole Principia is based on the idea of what force or set of forces will explain celestial motions and and terrestrial motions. And what is the law governing this force or these forces? That's his aim in the Principia. Not to explain why these forces work. That's for another generation or more to do. Okay. Now, the pragmatic and aesthetic views. I'm going to treat these together. Look, the pragmatic view says, here's James Clerk Maxwell for you. The pragmatic view simply says simplicity is a useful device. Doesn't necessarily give you the truth, and he'll give you, and Maxwell was very much concerned with this because he was concerned to develop kinetic theory in 1860. His first very famous paper, Illustrations of the Dynamical Theory of Gases. This is the one in which he develops the molecular distribution of velocity law named after him. And he says, look, I'm going to start with very simple assumptions. I'm going to start with the assumption that gases are composed of spherical molecules, okay? And I'm going to start by assuming that these spherical molecules are in motion and are only subject to contact forces when they hit each other or when they hit the sides of the container. I am not going to assume that there are intermolecular forces that are other than the contact ones, okay? I'm not going to assume there are any electrical forces or any gravitational forces here. And let's see where this leads. That was his problem. His question was really this. Is it possible to develop a mechanical theory of gases? That was his question. He didn't know whether it is, so he fools around with it. He called this an exercise in mechanics. And he set up these fundamental assumptions. And if you ask Maxwell, well, what's your justification? He said, well, look, I don't believe these are literally true. It's just, these are simple. And the mathematics is relatively simple here. And I'll see where this leads and how far I can get. And some results he gets the ideal gas law. He doesn't get the ratio of specific heats of gases. He's worried about that. But his main concern is to make the assumptions as simple as possible, just to see whether a mechanical theory of gases is possible. And if you ask Maxwell, well, does simplicity mean it's true? Maxwell would have said, of course not. It's just a useful device to see how far I can get in fooling around in this exercise in mechanics. Okay, all right. And I think this is the right answer here. The simplicity has nothing to do with truth or probability. It just has to do with the pragmatic idea of ease of use, of using a simple method to just start an investigation. Okay. Now, the final view, and I think that is perfectly legitimate, the final view is the aesthetic view, where we like beauty and simplicity is one criterion of beauty and so on. And that's fine, too, as long as you make no assumptions that a beautiful theory, a simple theory, a unifying theory is going to be true or even probable. In fact, you've got tension here. The more simple the theory, often, the more improbable it is. The more complex, I shouldn't make a generalization here, but often it's the case. The simpler the theory, the more, things as with Maxwell, you're ignoring intermolecular forces here. And so you get a simple theory at the cost of truth here, or literal truth, or complete truth. So it's a trade-off. Both have their value. The simplicity thing has this pragmatic value, and truth has the complexity in this case has its value. So it's a trade-off between the two. That's my sermon, and I'm sorry I can't be more metaphysical for you or give you this happy result of simplicity, giving you the truth of things. I'm ending up as a pragmatist, which is where I want to be, because I'm at Johns Hopkins University, where the first pragmatist actually came from, Charles Peirce. So I'm happy to be in that position and tell you as my thesis, that simplicity is largely mathematical.
So we have a little time for questions.
Before I ask the question, just a little anecdote about Einstein and simplicity. He was said that he gave a talk for students, a talk about simplicity of the equation, simplicity of nature, and then one student raised their hand and said, "But what happened, Professor Einstein, if nature is not simple?" And Einstein's answer was, "Well, then I'm not interested in." So, and this brings me to my question about this undetermined. Of course, as Einstein said, they are from the level of the observation. There is no logical way to a theory. There's no logical way. So there's always a maybe irrational jump, so to speak. And this is not unique, as you pointed out. But suppose we have a theory which copes with all the experimental observation which we have. Then there are many equivalent theories which also cope with this, which are maybe just mathematical mappings, but which do work with different concepts. And I agree that the question is, which one do we choose? And then the answer is the simplest one. Why do we choose the simplest one? Because we can elaborate, we can work better with the simplest one. We can extract information, maybe new information for new observation. So this supports your pragmatical point of view. So the idea is whether nature is simple or not is, we're looking for a simple description. We're looking for, and of course one must say we're quite successful.
Okay. Look, what Einstein said is exactly what you said. That is, there's no logical leap from the evidence to the theory. And the only sense I can make out of that is that there's no deductive leap. That is, there's an inductive leap from this. And of course, with an inductive leap, that means there's no conclusive proof of any theory. The theory based on all the evidence. I mean, Newton pointed this out with his law of gravity. Look, I've given you, based on all the evidence I have, I've concluded that the law of gravity is true. But if new evidence comes in that questions this, let me know about it. So, okay. But the point is, Newton's point is he thought he was in a position to say that the law of gravity is extremely probable. It's as certain as you get in what he called experimental philosophy, that is, experimental science. You don't need simplicity here. You can get the law of gravity without any of Newton's 4 rules of reasoning. I don't need to assume nature is simple to say, look, based on all the evidence I have, I can show you that the law of gravity holds. Okay, an inverse square law is the only law that will give me that I know about that will give me Kepler's laws. So and when you say choose this, there are various formulations, equivalent formulations of this, and you choose the simplest one. Well, that's okay. If they're equivalent, choose the one choose the formulation, the mathematical expression of it. That's the simplest for you. If you like Cartesian coordinates, use those. If you like polar coordinates, in this example, use those. But this is not a matter of which coordinate system is true. Okay, it's a matter of just which expressions, if they're equivalent, which expressions you like to use. That's okay. That's not what Einstein and Duhem meant, though. They really meant that somehow you're taking a leap of faith when you go from the empirical evidence to the conclusion. Newton was making a leap of faith as if this was irrational, except for the idea of simplicity. And that's what I'm questioning. Okay? It's not a leap of faith for me to go from a biased coin experiment to the claim that, well, it's 90% biased towards heads, so I believe heads will come up next time. That's not a leap of faith. That's just straightforward induction.
Yeah, I think we have time for one more question.
It's not a comment and question. I think if nature were not simple, then we couldn't possibly use mathematics to describe physics. And this is what probably Newton meant, because he developed the mathematics for physics.
Yes. But look, Newton could not. Newton treated the motions of the planets as a two-body problem. Okay, and because even three bodies very difficult to use the mathematics, and beyond that, almost impossible. So it's not just that if nature is simple, we can use the mathematics. Nature is quite complex, and then we develop a new mathematics, statistical mechanics was developed. We can't put a measure on each molecule in the gas, but if we can treat this statistically, we can proceed here. So I don't, I guess I'm objecting gently to the idea that we need to use mathematics. Mathematics presupposes simplicity. No. Life insurance companies would go out of business if they had to know when you're going to die to give you a life insurance policy. They rely on statistics.
Okay. Okay, let's thank Professor Achinstein once more. That helped me with my problems about understanding simplicity. Thank you. Yeah. So Sascha, 20 minutes, we start.
Can you hear me?
So I will introduce it. Can you flip that over? And I flip mine on. So when I'm on, you're off, and when I'm off, you're on. Okay, I'd like to introduce Sascha Husa. He's from the University of Mallorca, and he got his PhD in 1998, and I understand that he was a student of Professor Eichelberg, who gave the first talk on Monday. Sascha has worked in modeling space-times which contain black holes, and also modeling how gravitational radiation will occur in the space-time when you have collision or coalescing of black holes. And his talk is from Einstein's theory to identifying the sources of gravitational waves. Sascha.
Okay. Okay. All right. So thanks for inviting me to talk here. So what this talk intends to do is to build a little bit of bridge between the talk about the beauty of relativity that Peter Eichelberg has given on Monday, and the nice talk that we've heard this morning by Benno about the observations. And so what I'm going to talk about is the connection between these observations and calculating from Einstein's theory what we may see. So let's start with a brief review of Einstein's theory. And so Einstein's theory is built on very, very simple principles, very aesthetic principles and symmetries, like in particular the equivalence principle, which tells us that all masses fall the same, or that there's an equivalence between gravity and acceleration, which led Einstein to this far-reaching thought that gravity can be described by the curvature of space-time. And it's encapsulated in the Einstein equations, which are here written down for vacuum. And somehow from these Einstein equations we have to get to the observational results of the first gravitational wave detection, which they look, in details, look something like this. So what you see here is plots of probability distributions. For example, here, the first mass in the binary black hole, the second mass in the binary black hole with the most likely value. You see of these about 30 solar masses for each component, and then error bars. And also you see here there's something interesting. So there's actually different curves. It's like an overall curve. And then there are two kind of similar but not exactly the same curves, which are here called the IMR-P phenomenon and EUBNR. What are these things? These are models of the solution of the Einstein equations, which are used to determine these, to compare with the data, and they're used to determine these results and give us these values and give us these error bars. And what I'm going to talk about now is how do we get from the symmetries and the beauty of the Einstein equations to deriving these models and comparing them with the observational data. Benno has summarized very nicely this concept of hearing gravitational waves. I just want to mention this again very briefly. So, as you've heard, space-time in general relativity is a deformable entity, and heavy masses moving very rapidly, they can deform space-time and send ripples at the speed of light through space-time, and these ripples, they carry with them information about the sources, and this information we want to decode to make our observations. And the most efficient sources of gravitational waves are black holes. Why? Because they're the most compact objects in nature, and the more compact your objects are, the closer you can put them together, the faster they move around each other, and the more gravitational waves they emit. Now, prior to gravitational waves, basically everything we know about the universe we know from electromagnetic observations, like this one, and what they give us is a picture of the source. So what does this mean? It's because in electromagnetic observations we typically observe waves, electromagnetic waves, which are a superposition of many particles, an incoherent superposition of, because of this, we lose the phase information, and what we can observe is basically the angular dependence of the intensity coming from different regions of the sky, the intensity and, say, the color or the spectrum. And this is what gives us a picture of the source. Now, in gravitational waves, we get the full phase information. We can observe the full wave train with all the information intact, because this is the electromagnetic analog would be to just observe a single atom, except that in this case our single atom is two black holes at 70 solar masses orbiting around each other. And it's because of this, because gravitational waves, to give us information about the bulk motion of the objects, they are so analogous to hearing sound. And so we can, if you want to be poetic, we can talk about hearing the gravitational waves. They give us the soundtrack of the universe. Now, the interesting thing for the science, of course, is how these waves, how these sounds, which we've heard before, how do they encode the information? How do they encode the masses, the spins, and maybe new physics? Maybe we'll discover decoding this information, that actually we have to go beyond the equations of Einstein. How do we do this? So we've seen this before. I want to show this again. So these are the data which have actually been recorded in the two detectors, and here we see the theoretical prediction actually with the error bars here. This is why this line is a little bit thick, and it says numerical relativity. What does numerical relativity mean? Well, we put Einstein's equations on computers and we solve them with modern numerical methods on the grid, essentially. And then if we subtract this signal from the data, what we get is this, which is essentially just Gaussian noise, just random noise. And we can convince ourselves that there's no more information left, that all of the information about the signal has been extracted through this model of the source, the solution of Einstein's equations. Now, in order to understand a bit better what's actually going on, we have to understand a little bit about what's the anatomy of black hole mergers. How do these waves work out? So you have schematically pictured such a wave train, and basically three regimes which we can distinguish when the two masses are very, very far apart from each other. They will emit gravitational waves with very little, and you essentially have an adiabatic, very, very slow in-spiral. And you may see many of these cycles in your observation, and there's a perturbation theory to calculate the signal. It's called post-Newtonian theory, and it's basically a Taylor expansion in the velocity of the sources divided by the speed of light. And when the sources are far apart from each other and the velocity is small, this works extremely well. It has been used, for example, to analyze the data from the binary pulsar that has also been mentioned before. The problem is that when the sources come closer together, this doesn't really work anymore. So somewhere here, somewhere in the last orbits, this expansion breaks down. It doesn't work anymore, at least not accurately. Then we have to do something else. We have to solve the Einstein equations without any physical approximation, without doing a Taylor series in a physical parameter. What we do instead is essentially we use a non-physical expansion parameter, which is the grid size, in which we can study convergence, and we solve the Einstein equations as partial differential equations on a big computer. These are very expensive simulations. And then we can compute, with this method, we can compute all the way to the merger as the black holes merge together. We get a big spike in the waves which are emitted, and afterwards there's a phase of what we call ring down. It's basically damped oscillations, which again we can treat analytically by some kind of perturbation theory, which allows us to compute these damping frequencies here, but it doesn't allow to compute the amplitudes. For the amplitudes we have to use this numerical method and use the big computer simulations. And in this last region here, merger and ring down, this is also where most of the energy released is released. Up to 12% of the total mass of the binary is released to radiation, to gravitational waves within just a few milliseconds. Now, how do we actually now identify the signal in the data? Benno has talked a bit about this before. I want to give you a simple analog, and so the optimal analysis of data from gravitational wave detections, it relies on a mathematical method which is called matched filtering with template waveforms. And I could write down some equations and integrals and explain it this way, but I want to give you an explanation with a little analogous explanation. So you might have skipped a lecture or two in this conference, and you found yourself sitting in some cafe in Vienna, and so there's some music that you hear in the cafe, and you think, well, maybe this is Mozart, I'm just not sure what exactly it is, or maybe this is somebody else, and you want to find out what is the music. And so many of you, they would have an application on their smartphone with which you can record the music, and then it would look up in a database of basically all the musical pieces that are available, which is the one which matches best. And there are sophisticated algorithms in place to deal with the fact that you have to filter out the background noise in this cafe, maybe very noisy, or even instead of recording some professionally made music, maybe even you sing it yourself. And there's this music which I have in my mind. I want to know what kind of song this is. You sing it yourself, not quite correct, but the algorithms will find the best matching signal and tell you this is the most likely one, this is the second most likely, and so on. And what we do for gravitational waves is just basically the same thing, except that the songs are the waves which actually come from the universe, and the database is something which we have to create by ourselves by essentially computing all the possible solutions of the Einstein equations of interest, making a big database of themselves, and then comparing which is the best match. And this is the simple picture of how this works. Alright, so now we have to solve the Einstein equations. So they're beautiful. Every relativist is in the field because these equations are so beautiful. However, if you start to actually work on them, you discover, you expand them in Christoffel symbols and do many complicated things, you discover that actually behind the simplicity there's a lot of complication. The simple idea which is behind this is that basically the Einstein equations, general relativity, doesn't give you a preferred coordinate system. It's your task to choose a coordinate system, and once you have found one and you cast these tensor equations in this coordinate system, expand everything out in detail, you get very complicated, coupled, nonlinear partial differential equations. However, the nature of these equations is not unique. It depends on what kind of coordinate system you choose. So this is very unusual in physics. You should say, well, this problem is hyperbolic and this is parabolic or elliptic. And the Einstein equations, they have no fixed type. It depends on you, how you write them down. Very complicated. So you may get discouraged and you say, well, can I find solution? Can I find exact solutions? And you can, in the presence of symmetries. If you have enough symmetries, they simplify enough that you can actually find solutions. And the first very important one, and the very important one, the time-dependent vacuum spherical symmetry found by Schwarzschild just 1 year after the theory was presented very fast. It took 50 years to generalize this solution which describes non-rotating black holes to rotating black holes. And that's a long time. So this represents essentially all time-independent astrophysical black holes in the universe. And very interestingly, this has only two parameters. It's something that's really, really simple. It only has as parameters the mass and the angular momentum. There's also lots of families of cosmological solutions with symmetries, but for most of those it's not very clear how they relate to reality. You can also ask a different question. Well, can I find a systematic way of solving the Einstein equations? In particular, can I write them as an initial value formulation? Can I say, at time t equals 0, I have my gravitational field, and now let the equations tell me what's going to happen later in time or earlier in time? Can I do this? For classical theory of physics, I would certainly expect that to be true. And again, it took until the 1950s to give the answer that yes, this can be done. Unfortunately, there's not just one such formulation, there are many. You have to choose which one fits you best. And also, any such formulation has to break the beautiful symmetry and relativity between time and space, because you choose out some time coordinate in which you make your exploration of the space-time, and so some of the initial beauty has to get lost if you want to calculate something. Now, as I'm sure you've heard on the Monday lecture, general relativity is, as all the other fundamental theories of nature, is the gauge theory. It's the gauge theory of the diffeomorphism group, or the group of coordinate transformations. And so this means that there's no natural coordinate system. You're up to choose your own. And obviously, for example, if you have a very simple gravitational field, but then you represent this in a very bad choice of coordinates, your gravitational field will look very complicated. It has steep gradients. It will be very hard to find a numerical solution. So your choice of coordinates is crucial. Also, because it is a gauge theory, what this means in practice for somebody who wants to compute solutions is that the number of the computational degrees of freedom that you have to deal with is always larger, in this case quite larger, than the number of physical degrees of freedom. Now, your physical degrees of freedom in a theory, they usually behave quite reasonably because they express directly the physics. But if you have unphysical degrees of freedom, then you are free to choose. They can do difficult things. They can behave in a complicated way. They can form singularities. So, because of this, essentially all the computational treatment of gauge theories is always prone to instabilities in your unphysical computational degrees of freedom. Also, so if you want a unique time evolution, then you have to do what is usually called technically in gauge theories gauge fixing. Here means you have to choose your coordinates, and you may make bad choices and inappropriate choices for strong gravitational fields, which again is prone to instabilities, prone to all kinds of technical problems when you put this on a computer. So there's just lots of problems already, and then on top of this, there's another huge problem, which is that essentially due to the equivalence principle, you can't really localize gravitational energy or mass. You cannot say, you know, how much energy is in this room and how much energy is radiated in this room during this lecture. You can only do this in an unambiguous way if you go all the way to infinity and you solve a global problem. This is very hard. Okay? So lots and lots of problems which are all due to the inherent simplicity and symmetry of the Einstein equations. And if this is not enough, the Einstein equations also have the natural tendency to form singularities, because basically gravity is always attractive, things tend to clump together, and things tend to clump together so much that the gravitational field becomes infinite and you form a singularity. Now if you want to solve the equations on a computer, computers don't like singularities very much, so you have to do something. And there are basically two paradigms that you can do. One is called excision. You cut a hole in your computational domain, just like here. And why can you do this? Because at a horizon, all the information goes inward, nothing comes out. So it doesn't really matter what you put into the horizon. So you can just cut out the interior, and you don't have to deal with the singularity. This is a simple idea. In practice, it's really, really complicated. There's another way, another thing that you can do. This is called singularity avoiding gauge conditions. What's here the idea? This is a space-time diagram, so time goes upward, and so one of these lines is the three-dimensional space at a constant time. Here you have your singularity. Now the idea is simple. Since I'm completely free to choose my coordinates and my time coordinate as I like, I can try to choose my time coordinates and I'll wrap around the singularity. I just slow it down. If my computer code realizes I'm getting close to the singularity, the gravitational field has become very strong, I just move tiptoe ahead in time. I just make very, very small time steps, and everywhere else I make large time steps. Again, the basic idea is simple. The practical implementation has lots of complications. And so while people started in the early 60s, in 1964, to first attempt the computational solution of the binary black hole problem, that didn't go too well. It took until the 1990s to have the computational resources to actually do this in 3 dimensions. There was a huge project called the Binary Black Hole Grand Challenge Project in the US in the late 1990s to say, well, now we have the computational resources, let's get many groups together, and we finally do this problem, we solve it, we provide waveforms for the just starting out LIGO community, and what they discovered in a few years of research is that actually they had no idea how this works. There were lots of instabilities, lots of technical problems. All the problems which I've listed before, they deeply involve how things work, and it was not clear at all, essentially as LIGO was going to be started to be constructed, whether we could solve the Einstein equations in 5 years, in 10 years, or it would take 20 more years to give you an answer. And then finally in 2005, through work of Pretorius and soon after by many others, quite surprisingly, the first orbit, well, it's more like a half or 3/4 orbit, people could suddenly do this problem initially with very, very coarse resolution, very poor accuracy, but suddenly they could at least take 2 black holes quite close together and just simulate the last half orbit before they plunged together. This had taken about 40 years from the first attempt to being able to do this problem, and since then, the last 10 years, there's been huge progress. And I can show you, this is one of the simulations that we did for a binary black hole, which is could be consistent with, it's not the most likely parameter, but could be consistent with the first detection. You see, what is plotted here is essentially the curvature of the 2 black holes. You see them as they come very close together, there is this, it's like rolling around the space-time and creating these ripples, which go off, get stronger and stronger until they start to dim down as you relax to occur black hole, and so now these waves are going off. You can see here actually different, if you look sharply, you can see different grids with different resolutions. You have to use mesh refinements, complicated methods to actually capture accurately all this dynamics. I'll show you another movie. Here you see these two black holes going around on their slightly precessing orbits. The green arrows are the spins of these black holes. They're low precessing. And I show this because, again, there's a very interesting effect of coordinates and symmetry. It turns out that these black holes, they move exactly the right frequency which you would expect from the gravitational waves, yet this motion is completely arbitrary. It's just a coordinate effect. So why does this arbitrary coordinate effect just come out right, as you would naively expect? And it turns out that the whole solution only works if your coordinate conditions adapt just in the right way to find the inherent symmetries of the motion, and technically they have to do this up to a rigid rotation. You fix your rigid rotation by your boundary conditions at infinity, and so by the properties of this coordinate condition, things have to get out just right. Now, so why did it take 40 years? Why is it working now? Why didn't it work before? There are many, many reasons for this, but I would just want to point out one that I think is really the key. And so this is a story of wormholes and trumpets. Some of you, they may be familiar with this depiction of the Schwarzschild solution. It's a wormhole topology. It's also called the Einstein-Rosen bridge. And it has basically two universes. There's an outer one, you're somewhere out there. And if you would go through the horizon, which you can't in this case, but if you would go through, you could get into another universe and get infinitely far away from the horizon. So this is quite well studied and an exact solution. And standard initial data that you put for your initial value problem for black holes, in fact, they do have this topology of this Einstein-Rosen bridge. So if you put two of these, they would kind of look like something like this. You have two black holes, you have two of these wormholes put together. It's just a very convenient way to present these types of initial data. In fact, in order to make this practical and not deal with this funny topology, you just compactify these things here. You just coordinates. So there's all this other infinity. It's just mapped to a single point. Okay, we can do that. That's known how to do this. And then in order to compute this, we do what we have learned in numerics, which is if you have symmetries, you make them manifest. If there are singularities, you just try to understand them, and you factor them out, and you just deal with something which is regular. However, and this was done, and it didn't work, because it was done wrong. It turns out that this is in fact not the appropriate time-independent solution. If you actually study things mathematically, you find out that what happens usually would be that this wormhole just spaghettifies, it becomes thinner and thinner in time, like is depicted here. There's a snapshot where this throat has become very thin, and as time passes by, this essentially breaks up in two pieces. Each piece looks more like a trumpet with an infinitely long throat here, and so the appropriate solution for this problem as your code evolves is this geometry, not this one. And so because you factored out the wrong one, it didn't work. You factored out a singularity which wasn't there, so this is an infinite error. This didn't work. As soon as you give your coordinate conditions the freedom to adapt to this solution, it actually worked pretty well. Apart from many other things that, of course, you have to get right. Now, so now we have some understanding of how the Einstein equation is actually solved. Now, how do we get to this? How do we get to these observational results? Here, these are measurements of the spin of the black hole. How do we get to this? So you see here that now actually there's just one of these models. Before it was two, because there's only a single model that is implemented that we can use to correctly, fast enough, give us the waveform when there are general spins involved. And I was involved in doing this model. This was one of my contributions. And so I want to tell you a little bit about this, because also this has a lot to do with symmetry, and it's quite beautiful. Now, it turns out if you have two black holes with spin, basically the spin is vectors, And if the spin is orthogonal to the orbital plane, it looks pretty boring. So the orbital plane is preserved, the spins go around each other, but not too much happens. But if the spins are not orthogonal to the orbital plane, like so, then they do this very, very complicated precessing motion, which is, for example, indicated up here or there in a numerical simulation, and you can get very, very complicated waveforms like this one. Okay? In fact, so what people have done, people like me, others, many others as well, what they've spent the last 10 years on is to create very accurate solutions of the Einstein equations and model the solutions when there's no precision. It has taken us 10 years, but we can do this now reasonably well. But there's no precessing parameter space, it just has 3 dimensions. And the total has 7 dimensions because it's 1 mass ratio and 2 spins makes 7, so still missing 4 of 7 dimensions. And so there was a lot of, even though in 2005 there was this big breakthrough, we can do numerical relativity now, there was a lot of discouragement because how are we going to explore 7 dimensions with numerical simulations? How are we going to do this? And so it turns out that actually it's pretty easy if you're willing to make some approximations. And the key is that the orbital timescale, the timescale of this orbital motion of the black holes, is much smaller than the timescale of this precessing motion. And what this means is that as acceleration motion creates gravitational waves, the gravitational waves which are generated through the orbital motion are much, much stronger than the ones that are created in the precessing motion. So for how fast these black holes go together, precessing motion actually has very little effect. Okay? What precession basically does, it wiggles your system around, so sometimes you get more radiation in this direction, sometimes more radiation in this direction, but if you would be in a co-rotating frame, if you move with the black holes, it would pretty much look like a system which doesn't have precession. Okay? And so this is in fact the way we can get an excellent approximation to precessing systems. We make a model, we find solutions which very accurately represent non-precessing systems, and then with not very large accuracy, like the accuracy which is given to us by perturbation theory, we just twist up the solution, we compute the Euler angles of rotation that we need from this post-Newtonian perturbation expansion, and we put these amplitude modifications in at the end. Okay? And so this works surprisingly well. The idea is quite simple. It wasn't done for a long time until we tried it, and we found out that this really works surprisingly well. This has restrictions which at the current accuracy of detectors are not yet crucial, unfortunately. So for example, there's a certain north-south symmetry that this doesn't affect. For example, if the spins are in a certain position, you will just radiate, because of symmetry reasons, you will just radiate more energy in this direction than in this direction, which means you also radiate more momentum in this direction than in this direction, and so your black holes will then move the other way. And so what this creates, we just skip some little details, is basically if you have a binary where the 2 black holes are not equal, but they're unequal because they have different masses or different spins, you have a picture like this here, non-equal black holes. And so basically you can imagine the radiation is beamed, but if the black holes are not equal, it's beamed in different ways. So in this instant, more radiation goes this way than in this way, and so the black hole will recoil in the other way. Now, of course, since the black holes are orbiting over an orbit, this will cancel out, but since it's also in spiraling, it will not cancel out exactly. And so you will get some net effect with which the black hole will move away. This can be up to a few thousand kilometers. You can imagine this like basically if you have a sprinkler which is broken, where where there's more water coming out here than there, your sprinkler is going to move across the lawn. It's the same effect. Okay? And so this is very interesting for astronomers because these effects can be so large. The black hole, the merging black hole, is basically kicked out of its host galaxy, and you can hope to observe this. There's a nice symmetry explanation of what's actually going on. The maximum configuration is essentially this one here. You have spins in the orbital plane, but opposite. And so as these black holes rotate, essentially this one will shove radiation and space-time with its rotation this way, into the wall, and this one does the same, and they do the same as they go around, and so more radiation goes this way than this way, and so the black hole will recoil in the other direction. And so I'll show you a little movie with this. Oops. Maybe I don't show you a little movie. Let's see. Works. All right. So there's a nice movie of this. You can see the motion and the spins, the orbital momentum, and then how much energy is radiated in each direction. So during the in-spiral, it's not too asymmetric, but as they merge together, you can see there's much more radiation goes in one way than in the other way, and then the black hole just moves away in the other direction. And so with this, just leave you with this last slide. This is a plot of current based on the 2.5 detections we have so far. What's going to happen what's our chance of seeing something in the next runs, which are labeled 02 or 03? Well, we have a pretty good chance. This is more than 5 strong detections, more than 10, more than 35. So we have a pretty good chance to see, for example, more than 5 strong detections in the next science run. And in the next few years, once we go into the science sensitivity, LIGO and Virgo will detect tens to hundreds of black holes. Very, very exciting discoveries. And so we are confident that we'll be able to choose to observe the real strong field effects of GR with all their complex consequences and gory in detail, and explore all the, on the same time with these complications, explore all the beautiful aspects and simplicity of GR. But to extract the information from the detected data, you've seen in Benno's talk, the detectors are getting better and better. Benno and his colleagues are working very, very hard to make the detectors better, so this puts a lot of challenge on us to make our models and our quality of the solutions of the Einstein equations catch up at the same rate to extract all the science that we can. Thanks.
So we have time for one question.
There are several competing theories about the large-scale topology of the universe. Can the discovery of gravitational waves tell us something about it?
Sorry. Okay.
So this one cannot yet, but of course there's the hope. As we discover more and more black holes and neutron star binaries, tens or hundreds, or with ET thousands, that reach further and further in the universe, that with this we can map better and better the history, the expansion history of the universe. And it's also, as Benno has said, there's this really, really big hope that we can directly detect gravitational waves from a time before the cosmic microwave background was emitted, that we can go very, very, very early, and that will be the only way of getting information about these early times, and really put to a very hard test all the cosmological models that we have right now. So that's the big hope.
Okay, there's a brief question.
The brief question is about the uniqueness of the templates, especially if the parameter space becomes large. Is it so clear that a given template is uniquely determined by its parameters, or could there be a set of parameters leading to the same template?
Thanks. This is a very good question. Indeed, that's a big problem. There's lots of degeneracies. So with all the physical parameters of the system, and at the same time what we call extrinsic parameters, sky location, inclination, and so on, there's a lot of masking of one parameter than the other one. And the standard example, for example, for the first detection is if I have 2 black holes with roughly the same mass, which have pretty much the same but opposite spins. The effect of these spins on the waveform almost cancels out. And the same thing is with precession if it's not too strong. It doesn't have a very strong effect on the waveform. And so if we would look in detail at this, the prediction measurements of the spin, you may remember that I just showed here like 2 spin parameters, but actually 7. It's because, in fact, 6 of the 7 we can't measure very accurately because of all these degeneracies. But so our models currently, they're still very simple. They're very restricted. We have to make them better. But the SNR right now is not yet high enough to observe all these, to break all these degeneracies. So as the detectors get better, and as the models become more sophisticated, the hope is to finally break all these degeneracies and measure all the parameters of the black holes.
Thank you very much.
Yeah, sure. Oh, sorry. No. Okay.
So when you're on, I'm on. So are you turning them all? Okay, I turn them. This is your title. Okay, good. So the final speaker is Dezső Horváth, and he's at the Wigner Research Center for Physics, Institute for Particle Nuclear Physics in Budapest, and also Debrecen, did I pronounce it correctly? The Institute of Nuclear Physics. He's in the area of the special relativity because he deals with experimental high energy physics, and Einstein's special theory of relativity is predominant in contrast with Sascha Husa's talk about general relativity. And he's particularly interested and has done a lot of work in symmetries and charge parity time reversal symmetries that he will tell us something about in this talk. So, Dezső, please.
Okay, so as you see on the clock, I have exactly 0 minute to present my talk.
No, you actually have more.
Yeah. So my job is to speak about antimatter spectroscopy. I shall introduce CPT invariance and test the antiproton decelerator at CERN, antimatter experiments. I speak a little bit about antineutrinos and the dark matter problem, and I won't have time to introduce the practical applications at the end. So,
I will say this 10 minutes later.
Okay. So, the antimatter was born in 1928 by Paul Dirac, and now I connect to the first talk today because he wanted to have a simpler, nicer equation for the hydrogen atom, and so he drew a square root of a quadratic equation and got two solutions. He got two kinds of electrons. The ordinary electron with positive mass and negative charge, and the anti-electron, which later on was called positron, with negative mass, which was obviously wrong, and positive charge. Now, he assumed it is non-physical, but later, only 4 years later, Carl Anderson found the positrons in cosmic rays. So, the antiparticles are just as ordinary particles, apparently, as all particles, so it is a real existing particle. And so Dirac got the Nobel Prize in 1933 and Anderson in 1936. Now, apparently every matter particle, which we call fermions, have antiparticles. For instance, the proton, which is the hydrogen nucleus, has the antiproton. And they must have the same properties apart from the sign of the charge. So when a particle meets its own antiparticle, they annihilate to photons or to lighter particles. Of course, the energy has to be conserved. For instance, when an electron meets a positron, they annihilate and produce 2 or 3 gamma quanta. So the converse reaction is also possible. This is how we raise antiparticles when a high energy photon is involved in collision with, for instance, the electric field of an atomic nucleus. It can produce antiparticle-particle pairs. At lower energies, of course, it will be always an electron-positron pair, but at high enough energy, it can produce proton-antiproton pair. Now, there are several mysteries connected to antimatter. For instance, we don't understand why there is practically no antimatter in our universe. At the Big Bang, there was a radiation era, and exactly the same number of particles and antiparticles should have been produced, but the antimatter disappeared. Apparently there is no antimatter, what we could see in the universe. They could be hiding in parts of the universe inaccessible for us. Now I refer to the inflation theory. But there could be a tiny difference between particle and antiparticle to cause this asymmetry. It's a question. Another question is, are there particles which are their own antiparticles? We call them Majorana particles. The neutrinos could be, in principle, Majorana particles. And could the dark matter of the universe consist of such particles? We know that the universe has a lot of dark matter, and in principle there should be Majorana particles according to the supersymmetry theory. Can antimatter be used for something in everyday life, or is it just an expensive curiosity for the fun of physicists? Now the CPT invariance says that if you conjugate charge, so you make antiparticle from a particle, you reflect the space, so they just turn around the space direction and turn around time, and you do it all together, then you don't change much of the physics. So it is an amazing thing in the basic assumption of field theory. If you apply all three, then you can mathematically treat the results exactly the same way. So, for instance, a free antiparticle can be treated as a particle going backwards in space and time. It is amazing, it works. For instance, an electron-positron annihilation is described mathematically as if an electron came in, radiated 2 photons, and then came backwards in space and time. And it works to any precision, this picture. It is more than that. Giving up this invariance, this symmetry principle, one has to give up something very basic. For instance, the locality of interaction, which means causality, or the unitarity, the conservation of matter, information, etc., or Lorentz invariance. So it is a very basic thing. Now, theoreticians in general are convinced that CPT cannot be violated. Once I organized a conference in Hungary about it, and I couldn't find a single theoretician who would give an introductory talk. They say no way. So anyways, nevertheless, there are CPT violating theories, and they have the motivation that above the Planck scale, new physics is possible. It's 10 to the 19 GeV, and Lorentz violation is possible. Or quantum gravity could give such fluctuations which cause Lorentz violation or loss of information in black holes, which means unitarity violation. All these, of course, are very, very tiny things. Nevertheless, the motivation for testing CPT at low energy is the Lorentz and CPT invariance test needs a quantitative expression with violating theory, and also low energy tests can limit possible high energy violation. So how to test it? The simplest thing is to compare the particles and antiparticles. The most precise such test is the comparison of the mass of the neutral kaon with the neutral anti-kaon, which is less, the difference is less than 10 to minus 18. The other thing is to compare proton with the antiproton, compare mass charge and magnetic moment, and a very precise, promising comparison is the spectra of hydrogen and anti-hydrogen. Anti-hydrogen is the atom which is produced by an antiproton and a positron. Now, these experiments going on at CERN, this is the accelerator complex of CERN, and the last Symmetry Festival I spoke about the discovery of the Higgs boson at the CMS experiment I am working. Now I speak about the antiproton decelerator here. That's the highest and this is the lowest possible energy. So there are many experiments going on antimatter at CERN. The antiproton decelerator, I shall speak about each of these a little bit. And plus CERN developed a space experiment to check the presence of antimatter in space. So let's start. Anti-hydrogen. Anti-hydrogen is a p-bar positron atom, and there is a very precise measurement, is the 2-photon 2s1s transition, because it is completely Doppler free. Not completely, but almost. So it can be measured as precisely almost as the anti-kaon pair. So this is an aim of the antiproton decelerator measurements to reach this measurement. Now how can we do it? First of all, we have to put the antiprotons into an electromagnetic trap, cool them, then cool slow positrons, mix them, and trap the antihydrogen, which is produced in a highly excited state, so we have to wait until it goes down. All help with laser de-excitation. This is where we are now, at the antiproton decelerator. So the next thing is to cool antihydrogen and do the spectroscopy, or to form an antihydrogen beam, actually this is already done, and prepare a mass or magnetic moment measurement. Now, I am in this Husa experiment. It stands for atomic spectroscopy and collisions using slow antiprotons, and I spoke about this, actually it was 6 years ago, at the Symmetry Festival. Anyways, we are at the moment, we measure atomic transitions of an antiproton trapped in a helium atom. So it is a helium nucleus antiproton electron system, and we can reach a few times 10 to minus 10 precision measuring the antiproton mass. So now we are almost at the mass of the proton at this precision with this. So we are finishing this measurement because we reached the edge, the end of it. The alpha experiment, the antimatter laser physics apparatus, it's we physicists invent nice names for our experiments. They are the leaders of the anti-hydrogen business. They managed to tap already anti-hydrogen atoms for 1,000 secs. They induced a resonant hyperfine transition. They put a limit on the anti-hydrogen charge, and have a proposal for gravity measurement. This gravity is a hang-up at the antiproton decelerator, you will see. E-trap, it is the antimatter trap collaboration. They use a vertical experiment, that's the only one. All the other experiments are horizontal. They can produce a continuous antihydrogen source, and they measure the p-bar magnetic moment by spin flip in a pending tub with the precision of 1, 2, 3, 4, 5, 10 to minus 5. The other experiment is based, the baryon-antibaryon symmetry experiment. You see, it's a very nice abbreviation. And they repeated, they measured first of all, they checked the CPT by the charge over mass comparison of antiproton and proton with the precision of 10 to minus 11, few times 10 to minus 11, very precisely, and measured already the proton magnetic moment by 2 orders of magnitude more precisely than the previous measurement. So we are now waiting for the antiproton, similar antiproton measurement. The Aegis stands for antihydrogen antihydrogen experiment gravity interferometric spectroscopy. They are producing, or this is not yet done, but it is well on the way, antihydrogen atoms using not positrons but positronium atoms. This has the good thing that the antihydrogen will produce in less excited states than in the previous positron-antiproton collisions, the three-body collisions. They will, of course, remove the charged particles and let the antihydrogen beam into a Mohr deflectometer and compare the movement of antihydrogen through antihydrogen atoms with that of light, and this way they measure the gravitation of antihydrogen. Nobody believes that it would be different from hydrogen, but nevertheless this is one of the things which one has to check. G-bar, that's another gravitational experiment. They will produce charged, so they want to produce want to put 2 positrons on the antiproton. This way they can cool the charged antihydrogen atoms, then take off one of the positrons, and this way they want to drop them. Again, a gravity measurement. Asakusa, our experiment, produced an antihydrogen beam already, which is led out of the trap. We call it Musashi, monoenergetic ultrasonic antiproton source for high precision investigations. He was one of the most famous Japanese samurais, actually. And so that was many steps until we got to this stage. And now we have already the antihydrogen beam formed. The next thing will be to measure the hyperfine splitting of antihydrogen using a microwave cavity where we try to flip the polarized, positron polarization in antihydrogen and then check it. So this is an analogy for polarized light. Now, the next thing is at CERN is to build the extra low energy antiproton LN ring. This is already being constructed at CERN. All experiments will profit of it, and new experiments will be made possible with this new method. Now, the antimatter in space is studied by the alpha magnetic spectrometer, which was built at CERN for $2 billion. Of course, this is American billion, not European. It's big difference, 1,000. And it is launched in 2011 in the USA. Actually, it needed a big interaction of something with the American president to organize it. Something is the father. He's a Nobel Prize winner. This is the control room. It's control room at CERN, and it is put on the International Space Station here. And the first results were already disclosed. No anti-helium was observed. This was the key thing. So it confirms that no antimatter galaxies exist in the universe. There are high-energy positons anywhere, but it could come from dark matter or pulsars. It will collect data for the next 10-15 years. Now, the Majorana particles were introduced by Ettore Majorana in 1937. They must be neutral. They are particles which are their own antiparticles. And in the supersymmetry theory, the neutral supersymmetric fermions should be Majorana particles because of the degree of freedom. Yeah? The supersymmetry assumes that each fermion and boson in our universe, in the standard model, has corresponding particles with the other symmetry with exactly the same degrees of freedom. That's why the supersymmetric fermions have to be Majorana particles in principle, and they are very good candidates for dark matter. Of course, we are looking for them at the accelerators, but so far we couldn't find them. Now, the neutrino oscillation is also a very interesting thing. It is mysterious, as the neutrinos have only one interaction, the weak interaction, so they should not have mixed state in principle, but they do. So it is proven by many experiments, and last year they got the Nobel Prize, Kajita and McDonald, for proving the neutrino oscillations. The standard model has to be violated in order to have neutrino masses, because the massive neutrino means that there are right-handed neutrinos and left-handed antineutrinos which cannot have corresponding charged leptons connected to them. So we don't know, we don't observe such sterile neutrinos. We don't know why the neutrino masses are so small. We don't know how they are mixed. And we don't know whether the neutrinos are Majorana particles or not. So there are many, many neutrino experiments on Earth. I counted there are 17 completed, 34 working, 9 under construction, and 7 planned. So the conclusion is that the CPT invariance is very much confirmed by various experiments, but it is developing, and there are lots of future prospects, especially at the antiproton decelerator, but also by EMS2, and the search going on for heavy neutrinos, dark matter, and supersymmetry. Now, of course, there could be practical applications. It is nice and expensive physics, but the positron emission tomography is a very well-known thing. It exists everywhere, and it is a very typical antimatter experiment. At the antiproton decelerator, there is a so-called antiproton cell experiment which tries cancer therapy with antiprotons. The rocket fuel is a fantasy, and antimatter bomb is simply stupidity, but these are both well-known. So this is for me, this is an amazing result of positron PET. This is a normal subject, and this is a cocaine addict. One is surprised that this person is alive at all. that it has practically no brain activity according to the PET. And this is the antiproton cell experiment, which has the advantage that the antiproton lose energy in a very small volume and can be very well oriented, but disadvantage that they are very expensive and the annihilation radiation damages as well. Thank you very much.
No, just turn it off. So we have time for a question. Any questions? Yeah.
Can you say something about graviton? Yes.
Good. Actually, the quantum gravity is not my subject. I am a simple, poor experimental physicist. There are probably in this public people who are, but as you know, that the gravity cannot be described in the framework, usual framework of particles, the standard model, with the local symmetry, the gauge, with the local gauge interactions. So it's if there are of course attempts to do that, but it assumes a mediating boson which has to have a spin 2, and this is completely out of the standard model, and nobody sees them yet.
You have a very brief question.
Just a comment. Some years ago, I came across in the literature with papers on so-called positronium chemistry. So, although the lifetime of the positronium is very, very little, yet some chemical properties were stated to establish in such papers. This is just a comment.
Yeah, this is well known actually. No, okay. So positronium atom, the positronium atom, the electron-positron atom, has practically the same property as the hydrogen atom. It is just twice bigger because of the reduced mass. And there was quite a bit of studies, especially as this is a two-body system which can be very well calculated. The other thing is muonium, which is a positive muon-negative electron system, and that was also, it had also a lot of chemical applications. But then it just went out of fashion.
Thank you very much. There's a lunch break then till 1:30, 13:30. Thank you.